And there we go. Okay, welcome everybody to the May Technical Luncheon provided by Oklahoma City Geological Society. As a reminder, today's talk is going to be by a special guest, Dr. Jeff May, titled Using Sequence Stratigraphy to Optimize Target Selection in Unconventional Reservoirs. And as always, we'd like to thank our sponsors for their generosity in supporting OCGS. Allows us to provide these educational opportunities as well as courses that we're going to provide starting this month and on through the end of the year. And final shameless plug for the upcoming course next week. You can still sign up. We have a few slots available. It's on Applied Reservoir Engineering for geologists or geoscientists by Dr. Akutlu from Texas A&M. So if you'd like to do that, you can register through our OCGS page. If you have any questions, you can contact myself, Raleigh Bloomstein, or Chris Wiggers if you want to follow up with any questions regarding that course. And I'll go ahead and jump in and give a brief bio of Jeff's background, and then we'll hand it over to him. Okay. So Jeff received his BA in geology from Earlham College and his master's from Duke University, and then followed it up with a PhD from Rice University in geology. He's worked for over 40 years as a research geologist, starting out with Marathon Oil, then worked as a geologic and geophysical consultant with Enron Oil and Gas, and then moved over to GeoQuest Reservoir Technologies, and then worked for DDD Energy, and then finally getting to EOG Resources and started there as the chief stratigrapher and retired as the chief geologist in 2011. Since then, he's been acting as a geologic consultant and an affiliate faculty member with the Department of Geology and Geological Engineering for the Colorado School of Mines. And his focus in his research and in his oil and gas work history has been on sedimentology, sequence stratigraphy, and seismic stratigraphy projects in basins and fields worldwide. Extensive experience in the Gulf of Mexico on and offshore, and California on and offshore. He's worked all the sub-basins of the Rocky Mountain basin system, Permian and Williston basins. He's worked northern and eastern Egypt, Tuna Sea, Indonesia, and he's spent a lot of time leading classroom and field seminars on classics, deepwater sandstones, sequence stratigraphy, and mudstone deposition and stratigraphy, most notably for AAPG, the Petroleum Technology Transfer Council, and NODLS Worldwide, along with numerous oil and gas companies and universities. He's published numerous papers and abstracts on deepwater sandstones, sequence stratigraphy, geophysical interpretation, and mud rock deposition. He's received numerous rewards, including Best Speaker for the Rocky Mountain Association of Geologists, the Frank Kotlovsky Award for Best Speaker in the Energy Minerals Division at AAPG Annual Convention, and completed the AAPG Distinguished Lecturer Tour and received Outstanding Scientist Award from RMAG in 2017. On a personal note, Jeff's a great lecturer and teacher, and we're hoping to get him signed up for a course later this year to come here in Oklahoma City and share his knowledge with us. So stay tuned for that. Jeff, after all that, I'd like to hand it over to you and let you share your wisdom on sequence stratigraphy and how it can help us optimize target selection. So,
okay.
Appreciate you joining us once again.
So, where's my screen? Yeah, I know we practiced this, and now all of a sudden I couldn't find my screen. There it is, window. Oh, for some reason, sorry.
No, you're good. Did you hit that little up arrow and then?
Yeah, I hit the little under thing, and there it is. Oh,
I can do that.
all of a sudden, window isn't coming up. Let me do one different thing here. You know, you can practice as much as you want, and then something screws up. Share screen. I'm going back. There it is. Let's see if the window works. There it is. Got it. I had to move some windows around.
No problem.
Okay, can you see my window?
I can see it.
And the presentation, the PowerPoint.
Yes. Oh man,
and you can hear me.
Yes, you're in good shape.
Okay, here we go.
Take it away.
So as Raleigh said, I'm going to be talking about using sequence stratigraphy to optimize target selection in unconventional reservoirs. And I'll concentrate on sandstones and shales today. First of all, I acknowledge this talk has evolved from a technical presentation that Rob Diedrich and John McLeod had me do for SM Energy years ago. And I've just been collecting data and putting data, adding to it since then. You'll also see some materials from colleagues of mine at EOG, Terry Olson, Eric Kling, and Amy Nowak. To me, sequence stratigraphy isn't an end-all, be-all, but does provide another tool in your interpretation toolbox. And for the reasons that I list, one is that you can develop better well-logged correlations if you use sequence stratigraphy and chronostratigraphic surfaces as your correlation markers. It also can help you explore. It aids in prediction. That's exploration. It guides you when you want to collect data from cores in these unconventional reservoirs, and then provides a framework for integrating that data, the interpretation of that data. When you're working with reservoir engineers, sequence stratigraphy can help you develop better reservoir flow models and volumetrics. It helps you understand compartmentalization. It also helps you select and stay within the best horizontal targets. And finally, when you're working with your completion engineers, you can provide input to those engineers. So I'm going to go through 4 aspects today. One is using flooding surfaces to correlate pair sequences. Then I'll move to compartmentalization in high stand systems tracks versus falling stage systems tracks. Then I'll move to the relationship of hydrocarbon saturation and production relative to erosional surfaces, and then finish up with some shale examples, looking at the variability in reservoir mechanical properties within a sequence stratigraphic framework, and using that information to target the best horizontal zone. So this is kind of sequence stratigraphy 101, just so we're all on the same page. So during the late rise in sea level, you develop a high stand systems tract where you have shallow water systems prograding out basinward. Then during the initial fall in sea level, those shallow water systems move out and down into the basin. As wave base also drops, you impinge upon the underlying shelf deposits, and you get one or more surfaces of marine erosion, these regressive surfaces of marine erosion, and you have an exposure surface on the top set beds. That's the sequence boundary. Then during the rapid fall of sea level, you may incise valleys. If your shallow water systems build out to a shelf edge and you have an oversteepened slope, you may have that sediment bypass into deep water fan deposits. Then during the early slow rise in sea level, you're still in the low stand. This is the late low stand systems tract. You still have this exposure surface, the sequence boundary, but now you start filling in the estuaries, these incised valleys, and if your slope comes to grade, you develop a prograding shallow water system, prograding complex or prograding wedge. Finally, when sea level rises up and over this exposed surface, now waves interact with what was the exposure. So you get transgressive erosion or transgressive surface erosion coincident with a backstepping of the shallow water systems. So that's the development of one sequence and the systems tracts that make up the sequence. Those systems tracts, in turn, are made up of parasequences. That's essentially the fundamental correlation unit. I show two examples here, a wave-dominated parasequence and a fluvial-dominated parasequence with those chronostratigraphic flooding surfaces capping each. And then down here in the little blue triangles, I show a succession of parasequences in the high stand systems tract, the falling stage systems tract. You cross the sequence boundary into the low stand systems tract, then to the transgressive systems tract, back to the next high stand systems tract. So there's sequence stratigraphy 101. So I'm going to start off by talking about using flooding surfaces as your basic correlation markers for parasequences. I'll show two Cretaceous sandstone examples, the Parkman sandstone, the Baxter sandstone, both from Wyoming. But before I do that, I'm going to ask all of you to think about this. If I gave you 3 well logs, these are just diagrammatic gamma ray logs, from landward to basinward, gave you those 3, how would you correlate them? Would you say, well, I think I'm going to do character recognition, and my flooding surfaces parallel each other. So I've got 1, 2, 3 coursing upward shore face deposits or parasequences. And essentially, it makes a layer cake of interbedded mudstones, sandstones, mudstones, sandstones, mudstones, sandstones. Or would you say, well, Jeff, give me some more information. What's the distribution? Is this essentially an extensive cross-section? So that now I might think about dipping cliniforms, where my flooding surfaces are diving into the basin from proximal parasequences to more distal parasequences. And so my shoreline sands are pinching out, these parasequences pinch out into the basin. This affects your horizontal drilling. If you thought that these sands were all connected and that this parasequence was the best, you would drop your lateral into that parasequence and tell the reservoir engineers that's all one big reservoir compartment, and it should be essentially each frac stage should be about equivalent to every other frac stage along that horizontal. But what if you thought that was the way it was, and it was actually this, and you dropped your lateral there? Now you might have more effective frac stages in the sands and poorly effective frac stages in the shales, and not understand why, if this were your model versus that. Dave Wheeler pointed out how important that was to make sure you're using those flooding surfaces and correlating your parasequences perfectly when they were doing horizontal drilling in Savageton Field in the Parkman Sandstone in the Powder River Basin of Wyoming. He pointed out that based on character recognition, it'd be very interesting to jump correlate from this parasequence to that parasequence, maybe that parasequence, up to that parasequence, jumping from sand to shale to sand to shale to sand to shale. The problem with that is that there are certain parasequences that are going to be wet in this field and some that aren't. The ones that are not wet, the reservoir facies, are going to be these distal parasequences of the lower shore face, where to maybe middle shore face, where you have bioturbated and interlaminated sandstones and mudstones. The wet facies are the big blocky parasequences, the proximal parasequences of the upper shore face and foreshore. So what he showed was that they were targeting this distal parasequence 2 right here on the well log and dropping into this oil-rich zone. They also needed to correlate properly because they want to know how much shale was above each of these parasequences, above each flooding surface, so that there was adequate shale for a horizontal frac barrier. If they miscorrelated and jumped up, say, from here to here in parasequence 4, landed too high, there was no shale break above, and they would frac up into these clean, wet sands and bring in the ocean. Another example of careful parasequence correlation comes from the Baxter sandstone in the Green River Basin. So going landward to basinward, I was working with a geologist who did a nice correlation framework. These are two flooding surfaces on top of the parasequences. The green and the red are flooding surfaces. Then he had another flooding surface at the top of the Baxter. The problem was when he was doing net sand, the parasequence at the top of the Baxter was thickening as you went into the basin. That's not how shorelines act. That's not how parasequences act. They should be thinning and interfering with shales in the basin. So something was wrong. So he had me look at cores, and there are typical parasequences. This is a partial parasequence, lower shore face to middle shore face, flooding surface, then back to shelf deposits. A lot of the other cores also showed a lower shore face overlain by middle shore face here and here. But notice one thing, in between these packages, there's this kind of lighter gray interval. It's got calcite-filled fractures. Someone put acid on here and acid over here and didn't clean it off. That's a no-no in my book. Those are carbonate-rich zones. They're tight. They give a resistivity and density spike. Well, why should they be sitting between the lower shore face and middle shore face? So I started looking at the regional correlation, and here are those spikes. This is on the neutron porosity and density porosity curves. You can also see it over here on the SP or gamma rate, the gamma rate curves. And looking at those also dive into the basin paralleling these underlying flooding surfaces. So I think there's one, two more flooding surfaces in here. And those carbonate-rich zones represent hard grounds or firm grounds that develop diagenetically at the seafloor. So instead of one parasequence thickening into the basin, you actually had 1, 2, 3 parasequences that were very progradational without much aggradation. And if you would drop a lateral in here near the top of the Baxter, again, you'd be going from parasequence to parasequence to parasequence with potentially shales in between. And if there's any gas trapped beneath these tight reservoir barriers, you might not frack down and produce all the gas that's available. So that's a couple examples of why it's so important to understanding parasequence correlations. Now moving to compartmentalization in high stand systems tracts and falling stage systems tracts. I'm going to show an example from the Viking, the Woodbine, and then a Sussex. So here's the Viking example. It comes from a field up in Canada. The geologist working the field correlated these sands and called it the main sand. Essentially, it was a progradational high stand systems tract. Then they went in and water flooded the system, and the geologist told the engineers, oh, you're going to get this big, broad sweep. Well, they didn't. They got a restricted sweep, and it seems to be some reservoir barriers or baffles in here that hadn't been accounted for. Going back and doing a closer detailed correlation, the geologist realized that there were some unconformities in here, one here, that created the barriers to the water flood. So now we have this compartment of a high stand systems tract with a series of deltaic parasequences. Sea level dropped. You had erosion across this regressive surface of marine erosion. You developed some parasequences there, dropped again. You developed a second erosional surface. So now we have 1, 2, 3 reservoir compartments. And the sweep was between these two erosional boundaries. And then the top seal was the sequence boundary and transgressive surface erosion that merged above. I used that concept, that idea, when I was working at EOG. We were looking at the AA Wells Field in Texas, Woodbine sandstone. So this is landward to the right, basinward to the south. So I'm switching it up on you here. One thing I noticed was that as you went landward, what happens to these blocky sands. You lose the sands as you go landward. Also, we had some cores that indicated these were deltas, but they're very sharp base. You'd expect them to be cleaning and coarsening upward. But instead, we have sharp base, blocky sands sitting basinward of shale, of marine shale. How do those sands get out there? The other thing we saw was that we had variable thicknesses along dip. Here's a thinner blocky package, a thicker blocky package, back to thinner, back to thicker. Well, I brought in some other data too. We had some seismic data. Again, landward to basinward, those same 5 well logs. And in between these wells, we saw these dipping reflections. So that's telling you there's some kind of surface that's separating these different reservoir compartments. And in addition to tell us they were different reservoir compartments, we had some pressure decline curves from 3 of the wells on that cross section. They had different pressures, different starting pressures, and they declined at different rates. So that's telling you they're compartmentalized. So here are those 3 wells with the pressure data. So thinking about all this and using that model from that Viking sandstone field in Canada, I think we've got a falling stage systems tract. We had a regressive surface erosion developed at the base. Sea level rose a little bit, you had deposition, fell again, another erosional surface. Rose a little bit, you had deposition, fell again. Deposition, then fell again. So we've got now 1, 2, 3, 4 surface erosion. We can actually resolve those on the seismic data, those dipping reflections, and it explains why, for instance, this reservoir is not in communication with that reservoir, is not in communication with that reservoir, because these are barriers to fluid flow, barriers to reservoir pressure. And then again, the top seal is that merged sequence boundary transgressive surface erosion. Well, in both the cases I'm showing you, these sandstones were laterally adjacent to one another. That's not always the case with these falling stage packages. So they may start out that way, like is shown here. We drop sea level from sea level 1, 2, 3, 4, 5, 6, and 7. They are laterally adjacent to each other. Here are those blocky sandstones that thicken, thin, thicken. They have variable thicknesses as you go into the basin. But then the ensuing transgression can remove and winnow out those shore face sandstones, leaving behind some sands out in the basin. You also might get a pebbly lag, like here. These are chert pebbles with open marine mudstone below, open marine mudstone above. This actually comes from the Milk River Formation up in Canada. As far as I know, chert pebbles don't float. They don't fly, they don't swim. So how do they get out there? Well, they get out there during the falling stage of sea level and were left behind during the transgression. If you ever see that in core, think about that there may be a sand package, there may be a play out here farther basinward. That's what we did in the Milk River. The other thing that can happen is during transgression, those sands can be reworked long distances by waves and tides. And that's exactly what we see on these shelf sand ridges all around the world. Like here on the East Coast, we see it on the Gulf Coast. We see it in the Celtic Sea and the North Sea Channel. We see it on the Sunda Shelf in Indonesia. We see it in the Yellow Sea. A lot of the shelf deposits present today started off as falling stage and low stand sands that were reworked by waves and tides, often long distance, sub-parallel to the shoreline. So the flow of these waves and tides goes from an upstream edge to a downstream edge and reworks the sands. It cleans them up so that the bar top or the shoal top or the ridge top, use the term you like, are cleaner, cross-bedded. Then as you go downstream, so you've got an upstream erosional edge, and downstream you get into a thinner bedded sandstones and mudstones and bioturbation, all sitting over this regressive surface of marine erosion. Essentially, that's what I think is happening for a lot of these shoreline, paleo shoreline, parallel, elongate fields we see in the Western Cretaceous Interior Seaway. This is the Sussex. It would be the same model for the Hygiene or the Shannon, where you've got these basin-centered, elongate sand packages that become shaly and pinch out basinward. Then you develop another one, and it pinches out basinward. How do you get those? I think you drop sea level. You drop sea level down, you have this regressive surface of marine erosion. It's truncating underlying shale markers. The sands that are productive up here become shaly as you go distal. Then you had another drop in sea level, forming a second erosional surface, again, cutting out some of these markers. So we've got these two reservoir trends, the Hornbuckle Spearhead trend and the House Creek trend. I'm going to zoom in on the House Creek trend on the next slide. So here's 3 wells in the House Creek where there's horizontal drilling going on in the Sussex. Here's that regressive surface of erosion. Sometimes the sands above are blockier, sometimes a little more gradational. If you show this to an engineer and you say, we're going to drop a lateral in here, something like that, are you going to tell the engineer that this sand is going to look like that sand, is going to look like that sand, and they're all going to be essentially one big compartment? Or are you going to explain to the engineer that no, there's going to be variability in here, depending where you are in this shelf ridge, this paleo shelf ridge? Because you can look at the cores. And each well is going to have a different porosity and permeability as you vary from cleaner, coarser grain, cross-bedded glauconitic sands in the Mandel Federal versus maybe a bioturbated, muddy sandstone here in the Government Miles to laminated, interlaminated sandstones and mudstones with rip-ups in the Empire Federal. That sand, if you perf that sand, it will not be the same type of production if you perf this interval versus that interval. So geologists have to get better explaining this variability in these falling stage packages and these different compartments that we see in these packages. So turning now to the hydrocarbon production and saturation relative to erosional surfaces, I'm going to show 2 examples. This one again comes from the Powder River Basin in Wyoming. It's Cretaceous sand, the Frontier and Turner. So looking at the frontier to the southwest here, we see some parasequences that downlap onto a surface, this blue one down here. The deltas then built out and down into the basin during falling sea level. So now we've got a second frontier deltaic package sitting right here. In some cases, it's sand on sand separated by erosional conformity. In other places, it's sand sitting on shale above sand with that same erosional conformity. That's one of these regressive surfaces of marine erosion. Then you come to this area where you lose the sand. This is the Mary's Draw area. Then you come out to Crossbow and Porcupine, and you pick up sands that have been called the Turner sandstone. But careful correlation shows that this parasequence can be correlated to this parasequence. This is just the distal end of that. This is the distal end of that. This is yet another parasequence that we don't see back to the southwest. Well, what happened in between here? Well, I think that's a sequence boundary and transgressive surface erosion that merged, that eroded out. And one question has been, well, is that an erosional feature? Was that a channel? Was that a subaqueous or seafloor channel? I don't necessarily think that's true. I like Rondi Martinson's interpretation of a lot of these piano key fault blocks in the Powder River Basin. Sometimes they're up, sometimes they're down. You can get deposition. If the block pops up, you'll erode it off. So I think that this was overlying a deeper fault block. It popped up, you had erosion, then dropped back down, and you had mudstone deposition above those sands. As far as horizontal drilling, the drilling engineers came to us and said, so we can just land our lateral parallel to the top of that turner. EOG was working in this crossbow porcupine area. And we pointed out, and Eric Kling did too, that I was working with, no, if you do that, you're going to jump from parasequence 1 to parasequence 2 to parasequence 3 to parasequence 4. Again, you're going to go sand, shale, sand, shale, sand, shale. A big chunk of your horizontal wellbore will have poorly effective frac stages. So our recommendation was find the parasequence that you think is best and stay in it. Don't try to stay parallel to some surface. Identify the chronostratigraphic package, the parasequence, and stay in that. Turning our attention to the Bakken, so we're up here in the Devonian of the Williston Basin in North Dakota specifically, we were looking at drilling Three Forks and trying to land our laterals in the Three Forks and understanding the differences in hydrocarbon saturation. So here's the Three Forks with the upper Three Forks sitting here. To the southwest, you go into the Pronghorn Sandstone and the Pronghorn Shale, then the Bakken Shale, the lower Bakken Shale. As you go to the northeast, you lose that sandstone, you lose the shale beneath an erosional surface. Well, how does that affect the Three Forks? So remember, I'm trying to optimize my drilling in the Three Forks. Well, let's look at that erosional surface, and what happens is you go from the southwest to the northeast. So this is the southwest. This is where the pronghorn is present. You go from the upper Three Forks to a sequence boundary and transgressive surface of erosion at its top. Then you come up into the Pronghorn Sandstone, the Pronghorn Shale, and you get yet a second sequence boundary and transgressive surface of erosion. It looks very different when you go to the northeast. To the northeast, what happens? The Bakken Shale is sitting on the Three Forks. What happened to the Pronghorn? This upper sequence boundary kept cutting down, cutting down, cutting down until it merged with this lower one. So it cut out the Pronghorn Sandstone, cut out the Pronghorn Shale. Now we put the lower Bakken Shale directly on the Three Forks. You can actually see some rip-up class of the Three Forks in the basal Bakken. Well, how does that affect hydrocarbon saturation and drilling? The lower Bakken Shale is a source rock. So where you have the source rock close to or immediately on top of the Three Forks, the Three Forks is saturated with oil. That's where companies have drilled the Three Forks. These are Three Forks penetrations here in red. And look where the production has been. It's been where the pronghorn, and this is overlaying on a pronghorn isopath. The Three Forks production is where the pronghorn is absent or thin, where it's less than 20 feet thick. Once the pronghorn becomes greater than 20 feet thick, in between the lower Bakken Shale and the Three Forks, the oil could not be expulsed from the Bakken Shale through the pronghorn into the Three Forks. The pronghorn is a thief zone. So when you get above 20 feet for the pronghorn shale and sandstone, a couple companies have tried it, had really poor results. And you can see companies have stayed away from this pronghorn thick. They've stayed away from drilling the Three Forks there because the Three Forks is not saturated. So some last examples. So all those examples were in sandstones. Let's turn our attention to shales. So how can you use sequence stratigraphy to understand the variability in reservoir mechanical properties and then target the very best zones in shales? I'm going to give you 5 examples. But first I'm going to say beware of diagrams like these from a couple different publications. So many times you'll see shale data that's been averaged. And why do you want to worry about that? Because it's an average. Shales are heterogeneous. So this averages a lot of reservoir properties like TOC, maturity, porosity, etc., as well as mechanical properties, Poisson's ratio and Young's modulus for these shale plays. Or this compositional ternary diagram, again, averaging the composition for different shale plays. These kinds of data have their place, these kinds of diagrams have their place, but they don't tell the whole story. Shales are variable. You've got variable lithologies. In part, that's due to this competition between extrabasinal or detrital input and intrabasinal or biogenic input. You can have this detrital input coming from the siliciclastics or carbonate systems as fine-grained clay-rich hypopycnal plumes or coarser-grained sediment gravity flows. Then you can have this biogenic material that's formed in the water column and drops out of the water column to the seafloor. Some of it is skeletal. It's hard grains, like here from forams or coccolithophores. Or you can have organic matter. That's a cell wall of things like bacteria, pollen, spores, algae falling to the seafloor, and fecal matter falling to the seafloor. So it's not consistent. As sea level changes, as circulation changes, that you get more extrabasinal versus more intrabasinal, and it cycles back and forth. You also get variable pore types and sizes and connectivity. So you've got organic matter pores. They may or may not be well interconnected. You get these really poorly interconnected intra-particle pores, like here, where we've got dolomite rhombs that are being dissolved out. Some of the best porosity in especially our oil plays in shales, come from interparticle pores, between particles. They tend to be larger, they tend to be interconnected. So where does all this fall into a sequence stratigraphic framework? And on top of this, you have to consider mechanical properties, the variable mechanical properties of shales. Some intervals are like cork. It's weak, but it can be strong. Or maybe more like rubber. They're weak and ductile. So on this cross plot of Young's modulus to Poisson's ratio, you go from low Young's modulus to high Young's modulus as you go from weak to strong. On the Poisson's ratio, that's brittleness. You go from ductile out here in a high Poisson's ratio to brittle here. So we tend to like shales that don't look like cork or rubber. We want them up here near the glass end, this upper northwest quadrant on this cross plot. But these are variable throughout any shale column. The shales will have big clouds of data in here. It's not just one single number. So like I say, beware of averages. You have this variability. And this variability, or this heterogeneity, may seem completely random. It's not. It follows a logical succession based on the development of your systems tracks in your shales. So now let's look at the sequence stratigraphic framework. Where would you be targeting the best reservoirs? And what would be the properties of those best reservoirs? So I put this together. I think the best shale reservoirs have intervals that are load-bearing or strong, high Young's modulus, and are brittle, low Poisson's ratio. And they've got to have large interconnected pores. And of course, hydrocarbon saturation. If your input is dominantly extrabasinal or detrital, you get load-bearing detrital grains coming into the system during high stands and low stands in both clastics and carbonates. But if your system is dominantly biogenic or intrabasinal, these load-bearing grains are not detrital, they're skeletal material. You don't want a lot of detrital material. That would simply dilute this. The clays and silt would dilute your skeletal grains. So how do you accumulate a lot of microfossil debris? It's during late transgressions and condensed sections where you don't have a lot of dilution. You also might get a lot of organic matter mixed in during this condensed interval. So here's some examples. I'll start with some of the earliest drilling, the Marcellus. Back in the mid-2000s, everyone was targeting the most organic rich interval in our shales. The Marcellus was no exception. The early wells went right down near the base here. You can see the gamma ray gets really hot. This is very organic rich, sitting right above the sequence boundary. This is a condensed section. But look at the production. These were either completely dry or uneconomic wells. Later wells were moved up 20 or 30 feet. You can see the completion intervals in here. So laterals were drilled up a little bit higher out of that organic rich condensed section into the early high stand. And now look at the IPs. These became economic. Well, why was there such a difference? Just 20 or 30 feet. The initial wells in the condensed section drilled rock looking like this. This is from the Marcellus. It's very organic rich. All this dark gray in here is kerogen and bitumen, but there's also a lot of clay. That's all these elongate flocks in here. That's all clay. So this is clay rich. It didn't have much in the way of interparticle pores. It did have some intraparticle pores, like around that dolomite rhomb, and most of the porosity were organic matter pores. And they weren't really well connected. But you moved up just a little bit, and now we see this is all detrital silt coming in. What did that detrital silt do for you? It essentially created shelter porosity. You had grains of sand, of quartz sand and feldspar that also sheltered, there's clay right there, but sheltered the clays from being compacted. So it preserved the interparticle porosity between these grains, between the silt grains, even between the clay flocks. So now we've got better porosity, better storage capability. In addition to that, these grains formed a strong, brittle framework. So two things happened by just moving up 20 or 30 feet. Better reservoir properties, better mechanical properties. Similarly, in the Eagleford, now the Eagleford is dominated by biogenic material, but there's an overprint of extrabasinal energy, waves and storm waves especially, reworking this material. So when EOG was first drilling the Eagleford, like a lot of other companies, they were drilling down deep in the condensed section, sitting right above the Buda sequence boundary. Here's what the rock looked like. This is the condensed section. If I just, these are where we took samples, right there. That is an XRD sample. It said it was 68% calcite, 12% quartz, only 14% clay. Man, early on we'd say that was a great rock, but it wasn't a great rock. We had sticking problems. This is what the well bore sounded like when we were drilling. It was, we had really low rates of penetration. We moved our well bores up just a little bit into the lower Eagleford, right? Something like that. And now we're in the early high stand again. Again, this is our XRD data right there. That was our data point. That's 50% calcite, 90% quartz, 16% clay. It doesn't look all that different. You'd say, well, if you just had cutting samples, for instance, and just had XRD data without looking at the core, you'd say, I don't understand why I have sticking here, but here when I'm drilling, it drills like a dream. Well, this calcite here, this is all foraminiferal sand, this laminated and cross-laminated intervals. The calcite here is clay size calcareous material and these ionoceramide debris. And it's not just the composition that created the drilling problems, but it was the fabric too. So the condensed section where we have the sticking problems looked like this. This is an EDAX of an SEM photomicrograph. So false color image. So the carbonates in here are in blue. That was our carbonate mud. It was in layers or sheets, interlaminated with sand and clay, clays in green. So you can see in this fib SEM that we've got a lot of porosity in a lot of organic material here in the condensed section and a lot of clay. That's kaolinite. But the clay was in layers, was in sheets. It was like trying to drill through a bunch of rubber sheets. We moved up a little bit into the high stand. These are the forams in the blue here with dispersed quartz silt and dispersed clay. So now we didn't have the sheets. So now we had a strong, rigid framework of carbonate and sand with interconnected interparticle porosity. That was the better target. Here's the Maori, and I'm working with a student at School of Mines, and she's come up with some great work on the Maori. We've subdivided the Maori, like a lot of people have, into the lower, middle, and upper Maori. It turns out these are 3 high-frequency, high-stand systems tracks. The total Maori only was about 1.5 to maybe 1.7 million years. So these are very high-frequency cycles. This is from the Bighorn Basin in Wyoming, where sands develop in the top of each of these cycles. Then you have a little transgression at top up to a maximum flooding surface there and there, which are actually the divisions that cap the lower Maori, cap the middle Maori of these condensed sections. Well, let's zoom in on this. Here we're not worrying about condensed sections. We're worrying about here, well, where do I land my lateral? Well, it turns out in each of these high stands, we start off with a more clay-rich interval. There's a core photo, thin section, FIB, SEM photomicrograph. And what we see is the early high stand packages have high TOC, but really poorly developed interparticle porosity, in part because of all the clay in there. You move up into the late high stand intervals. Now we've got, you can see all the silt in here. The silt again gives you kind of this shelter porosity. And now we see porosity developed between the clay flocks as well as associated with the organics. So here's some inorganic matter. So now we've got much better developed porosity that's interconnected, and the reservoir mechanics is better. I'll show that in this slide. So where do we want to target in these 3 high stand systems tracks? Well, it turns out this middle Maori interval has higher TOC overall. And looking over here, that middle Maori interval is where we have the better hydrocarbon saturation. But that's still a pretty thick interval. Where are we going to land our lateral? Does it matter? Well, when you look at Young's modulus cross-plotted with Poisson's ratio, some people call this frackability. That middle Maori section has the better frackability. So that's good. That still doesn't exactly tell me where I should land my laterals, but look at this. We actually are made up of a series of parasequences in here with flooding surfaces. These bentonites in between represent flooding surfaces. And it's this uppermost parasequence right there that has the best frackability. So where do you want to land your lateral? You land it up here. It's siltier at the top of that high stand. You've got better permeability, better porosity. You've got better frackability, and it sits right on top of this oil saturated zone, and the oil migrates up into this better lateral target right there. So now I'm going to mess with your minds. I'm going to change to an extra-basinal dominated system, the Niobrara. The others have been dominated, or extra-basinal, sorry. This is intrabasinal, or more biogenic. During transgressions to the condensed section, the deltas, the shorelines, retreated to the west, retreated to the east in this western Cretaceous interior seaway. You had mixing of warm Tethyan waters with cool boreal waters. You had oxygenation and mixing. You also had a lot of organic material, so now we have a high productivity. So what did we develop during transgressions and condensed sections? Develop chalk. It's bioclastic dominated. It's these light gray intervals. They were dominated by pellets, by forams, and coccolithophores. So you got a brittle rock, which is great. But we might have had high productivity and high organic matter, but because of the oxygenation, all the burrowing organisms, you can see the burrows here and here and here, it removed the organic matter. So that's what the chalks look like. What about during high stands? The deltas, the shorelines built to the east, to the west. This narrow neck, you had a shallow sill, it prevented the spillover of the warm Tethyan waters. We had this estuarine type of circulation. So we have these delta regressions and more detrital influx mixing with a biogenic component. So we got these marls. But because of the low oxygenation, the stagnation on the seafloor, this actually preserved a lot of high organic matter content. We didn't have a lot of burrowers to remove it. So which should we target? Should we target the chalks? Should we target the marls? The marls have more TOC, the chalks tend to be more brittle. Here's what chalk looks like in thin section with the forams and pellets versus the marls where phosphates and pellets, more laminated. Here's what they look like under SEM photomicrographs. We can see this interlocking calcite fabric of the chalks, even with some calcite overgrowths and big open interparticle pores. You go to the marls, you've also got a lot of debris, bioclastic debris. It's not really that clay rich. There is some clay, but you also have a lot of organic matter. And organic matter, it turns out, has these elongate slot pores in the oil window. So I'm still stuck. Do I want to go for the brittleness? Do I want to go for the high TOC, where I still have pretty much a pretty good amount of carbonate material? Well, let's go into a little more detail. Maybe NMR can help us. So here's my nuclear magnetic resonance logs. And I'm not a petrophysicist, so I had to rely on my friendly petrophysicist, Terry Olson. So here's a small pore, diameter X. So when you compress it, then relax it, you get this interval of fast relaxation indicating small pores. This bigger pore, 3 times the diameter, the equivalent circle diameter is 3x. If you compress it, then relax it, it takes longer to relax up in this zone. So this is the large pore. These would be kind of the equidimensional pores that you see in the chalks. What about these elongate pores that you see in the marls? Those elongate pores have a width of X, but if you go all the way around it, the equivalent circular diameter is 3x. So what happens? So we've realized that pores change their size and shape in different lithologies and maturities. But what is the NMR log telling you about these large pores? It's going to say it's a small pore. Because why? When you compress this pore, then relax it, the NMR log is record the fast relaxation across this narrow diameter right there. So if you just use NMR logs to help you try to target, you might actually be underestimating large pore porosity. So there's actually a lot of porosity in the marls. So I'm still stuck. Which one should I target? Well, let's bring in more data. So again, here's my chalk. This is the lower B chalk. It's a condensed section, more carbonate, less clastics. NMR log is saying it's large pores. That should be our main target. But down here in the marl, the most organic rich zone, so here's the attempt at this D log R showing that there's more organic matter. We don't know whether it's movable oil or not. Turns out it is a lot of movable oil. Some of it is also organic matter. In the high stand, we've got more detrital, silica and clay in the yellow and the gray. But the NMR log would say these are small pores. Well, I just showed you that the NMR log can lie if you've got these long, narrow pores. So maybe that should be a target. Maybe we should be drilling it. Keep bringing in data. Answer that question. MICP data. that tells you not the pore size, but the pore throat size. So the MICP data is showing us in the condensed section, these large pores have bigger interconnected pore throats. These large pores have much smaller pore throats. So which would you want to drill? I'd want to drill this one, where I've got better interconnected interparticle porosity and brittle rock. Final example here, just finishing up, is the Leonard, the Avalon in the Delaware Basin, just to the west of the Central Basin Platform in the Red Hills area. I identified 6 major facies: quartz turbidites, calcareous turbidites, debrites, also slumps, slide blocks, laminated mudstones. I worked with Amy Nowak, and she subdivided the mudstones a little bit more into laminated mudstones with high TOC, low TOC, carbonate concretions, and burrowed mudstones. What you find when you cross-plot permeability and porosity is that out here you've got big pores in a lot of these mudstones, especially the laminated mudstones, in the burrowed mudstones, as well as in some of these debrites and slumps and slides. So those have large pores, but not much permeability. Here we have small pores, but better permeability in our quartz and carbonate turbidites. Here's a photomicrograph of that, showing this interconnected, small pore, but good permeability rock in these turbidites. So it looks like we could have pretty good reservoir, but is it going to be one that we can frack? So going to the cross plot here, again, up here in this northwest quadrant, what do we see? Here's a lot of the carbonate turbidites. Here's a lot of the quartz turbidites. That looks like a good zone to target. So going and looking at it in core, it turns out all the silicious facies, like I'm showing here, where you have this conjugate fracture set, comparing it to my core description, the siliciclastic mudstones are in gray, the carbonate debris flows and slumps are in blue. The carbonate packages don't have any natural fractures. The natural fractures are in rocks like this, the siliciclastics. Okay, final image. Tie it all together. Talking to the completion engineers after I looked at the cores, after we did the cross plot information, after we did the mechanical work, here's where we're getting our carbonate and quartz turbidites in this low stand of the upper Avalon Shale and the lower Avalon Shale. That's also where we're tending to get this good interconnected porosity, good oil saturation indicated by our logs here and here. So my first recommendation was, well, this is the great target right there. But my question back to the completion engineers is, if we drill that, aren't we going to leave behind all that oil? And they said, yeah. So my question to them was, well, can't we just target the intervening high stand with all these slide blocks and slumps, poor porosity, but maybe just frack the bejesus out of it, frack up, frack down. And they said, yeah, Jeff, but wait a minute, remember your cross plot of Poisson's ratio and Young's modulus. It could be brittle, but it's weak. What's going to happen? You frack it, and then the fracks are going to close back up. So if we frack that, we're going to have really bad well results. So we need to target 2 separate intervals, high, and then stack our laterals and target low. So the bottom line here is sequence stratigraphy is not the answer. Some would say useful. I would say it's even a necessary tool when you're trying to understand your unconventional reservoirs and the horizontal targets. It gives you a better understanding of the controls on what's reservoir versus not reservoir. It gives you a framework to pick out what kind of data you need from where and integrating that data. It gives you a better way of mapping and correlating your horizontal targets, so you're not jumping from one zone to another. Working with your reservoir engineers, it gives you a better bottom line economic evaluation. it helps you define and stay within the best horizontal target. And finally, when you're working with your completion and your drilling group, it gives more input for them on what they should be targeting. So thank you very much. I appreciate it. And if anyone has any questions, I'm ready to answer them.
Hey, Jeff, thanks a lot. Great presentation. Looks like, let's see if we got some. Oh, we had a question on what MICP data was.
Oh, that's mercury injection capillary pressure data. So Chris, I think we're getting a little feedback. Okay, now it's better. So that's mercury injection capillary pressure data where they inject mercury into the sample. And I'm not an expert at it. I'm sure there's a lot of people online right now that could tell you better. But it's looking at the entry pressure of mercury, and it's looking at the rate at which mercury moves into the rock until you get 10% saturation. So by doing a lot of calculations, by having your friendly engineer do all the calculations, not this geologist do it, you can calculate, one of the things you can calculate are pore throat sizes. So that's mercury injection capillary pressure data. Any other questions, or did I completely muddy the waters, or was it completely clear?
No. There's one. Have you converted core data and utilized seismic to build an HRA model for additional targeting? So,
you know, a lot of that work was being done as I retired from EOG, especially in the Eagle Ford and even more so in the Permian Basin, where we had some good 3D data. So I've not done that. I've seen it done by different companies. I've seen some results, but I've not done that. But they've taken the core data like porosity, TOC, things like that, taking the log data, the petrophysical data, tying to the core data, then tying to the seismic data, and looking at things like impedance contrast, looking at your elastic your parameters, your Lambda parameters you derive from your seismic data to build your models to do two things, actually. One for sweet spot definition as well as for targeting. Any other questions? You guys are letting me off easy.
Giving people a shot here. Oh, here's the long one. I don't know if you can see that. For productive sand bodies in the falling stage system tract you discussed, are the aspect ratios for those deposits consistent or predictable along strike, or do they tend to be highly variable and difficult to chase as an exploration play?
I would say that they're more variable than they are predictable. And there's two aspects of that. One is that as your deltas downstepped in the basin or your shoreline downsteps in the basin, it depends on how wave dominated versus tidal dominated versus fluvial dominated it was. So elongate shoreline might end up giving you a more elongate sand down dip versus something that was maybe more cuspate or restricted, like a fluvial dominated delta that moves down dip. The second thing is that during the ensuing transgression, depending on how strong and how long lived those tidal currents, those wave currents are, you can move those, rework those sands and move them long distances. Gus Gustafson thinks a lot of the Cretaceous sands we see in Wyoming actually originated up in Canada and removed many tens, hundreds of kilometers along strike. So during that reworking, it can really affect the sizes and the aspect ratios of those sand bodies. So they're difficult to chase if you only have limited well data.
Okay, here's another one. For the natural fracture distribution that you showed next to the core description, is that a graphical representation of the fractures observed in the core, or is it reflecting the calculated fracture distribution?
Yeah.
Such
It's
as
not,
fractures per foot.
that's a really good question. When I describe core, I draw every single fracture, and I've got a system where they're closed or open, where they're filled, and what they're filled with if they are filled. So every single one of those little red little squiggles I had on there represented one fracture in that core, and I tried to indicate the top and the bottom, because a lot of the fractures might be bed bounded. I want to know that. But I can go back and use that data from my core description to then calculate fractures per foot. So, but those are actually the graphic representation of the observed fractures.
Okay, let's see. Is it possible to differentiate glaciostatic sea level fluctuation from tectonic movement?
Gee, thanks, John. The problem is, I would say ultimately, unless you have good worldwide data, especially good worldwide biostratigraphic data, it's difficult to break out glacial Eustace from tectonics. And usually what we're seeing along shorelines, what we're seeing in the outcrop, what we're seeing in core, what we're seeing in well logs, is, I always refer to it as relative sea level. It's the overprint of local tectonism, whether it's uplift or subsidence, on glacial Eustace. So a lot of what you're seeing is, you can't say that's purely glacial Eustace. It is the overprint of tectonics, especially local tectonics, on glacial Eustace. Ooh.
Oh, man, you got a flood of likes here.
I see the question about origin of dolomite in the shale. Boy, that's a good one. I really don't know. So I showed the dolomite, for instance, in the Marcellus. There's actually a lot of dolomite in the Mowry. One idea is that some of it might be hydrothermally related. Some of it might be originate shallow on the seafloor during interaction of your bacteria on the seafloor with the calcareous material coming down, the detrital material. That's a good question. I don't have an answer for it. The origin of the dolomite. I've seen different people put it together. That actually is one thing that this student I mentioned, Alexis Sociano, who's working on the Mowry, we do see a lot of Farrowan dolomite in the coarser grained laminae and intervals in the Mowry, in the upper part of those high stands. So, but I don't know, she's trying to put together the dolomite story, and I don't have the answer for that. Sorry. Keep in touch. Watch for, if you want to send me your email, I'll give you her email when she finishes up her work. So Khalid, if you want to send me your email address.
Hey Jeff, we got a question on the questions section from Presley. EOG is probably the gold standard in the resource arena. Has sequence strat been their approach from the beginning to identify drilling targets?
Oh, I'm trying to be politically correct here. EOG, when I first joined it, my boss was a gentleman by the name of Lauren Leiker. He was the senior executive VP of exploration. He actually took a well log sequence certificate class of mine that I taught decades ago for AAPG. I've updated it since, and that's actually the class that Raleigh mentioned that the Oklahoma City Geological Society is trying to bring me in this fall to teach for the Oklahoma City audience. So he was really interested in sequence stratigraphy. That's why he kept trying to get me to come over to EOG, and which I eventually did as the chief stratigrapher and then chief geologist. because he felt sequence stratigraphy, like I've tried to show you, is important in identifying drilling targets. And that's both from regionally, as far as sweet spotting, down to the vertical, where do you land your laterals? So sequence stratigraphy early on was very important in trying to understand what acreage to buy and where to land the laterals. We did use it, for instance, in the Mowry. I showed you the example of the Mowry. Why are a lot of wells moved up into the top of that middle Mowry high stand? A lot of other companies are doing the same thing. Chesapeake was doing the same thing. Devon was doing the same thing. So it's not just, and for instance, the Marcellus, moving it from the condensed section to the early high stand. Range Resources was the first one to do that. So it wasn't, so other companies understand the sequence stratigraphic approach. So I will say this to you, Presley. Yes, sequence stratigraphy was very important in identifying drilling targets early on. As the company has evolved and different personnel have moved in or out of different positions, I'm not sure it's as utilized quite as much today, although the chief geologist is very conversant in sequence stratigraphy. So I don't want to say that it's not used at all. I don't know how much it's used as it was in the past. It seems like as we've gone more into the mining or the industrialization of drilling, maybe we've moved away more from the early stages of using sequence stratigraphy to identify targets. We've identified them. So at some point, how important is that sequence stratigraphic framework? I don't know. But I would say that yes, we did utilize sequence stratigraphy early on in trying to find different shale plays and figure out where the best zones were to land the laterals. Anything else?
Get everybody shot here.
Yeah. I was going to say thanks for everyone. It was a little bit over an hour with the announcements at the beginning, so I thank you for sticking with me.
Yeah, I think it was great. No, I appreciate it again, Jeff. And yeah, hopefully we can have you in town, I think hopefully in November. Yep. And we're just working on a venue. So always appreciative of getting some time with you. And yeah, hopefully we can make that happen in November. So
okay.
Thanks a lot again for your time for this lunch talk without the lunch.
Can I make one other comment? There is in search and discovery. So I split this into two separate talks for the Rocky Mountain section AAPG meeting. So on the AAPG search and discovery website, you can find a lot of these same diagrams. And the talk is on there.
Oh, that's great. So, all right. Well, I guess we should sign off. And also, we always publish the a video of this, so it'll be out there as well.
Okay, great.
You want to follow up and go through it again, or missed it and they want to catch it. So,
okay.
All right. Thanks again for your time.
Well,
always appreciate it.
Yep. Thanks for the invitation. Thanks everyone for attending. Appreciate it.
Thanks, Jeff.
Bye-bye.
Bye.
Bye.